Good morning, and welcome to the fourth Geopolymer Camp for those who arrived this morning. We had approximately 80 participants. Some are still missing. I guess they will not arrive. I'm presenting my state of the Geopolymer R&D 2012, that is to say what happened on the internet since the last Geopolymer Camp. We have recorded the previous state of the art Geopolymer Camp 2009, and it has been viewed more than 2,070 times. The Geopolymer Camp 2010, more than 800, and the Geopolymer Camp 2011, that is younger, more than 500. This is on the internet, and it lasts 50 minutes, 1 hour, depending, but it is always very interesting. So the state of the geopolymer research and development comprises 4 parts: geopolymer science, geopolymer technologies, geopolymer cement and concrete, and geopolymer and archaeology. It is interesting to follow how long it took to emerge from a very remote project that started here in Saint-Quentin 35 or 40 years ago, and to reach the level of worldwide science technology. At our first Geopolymer conference in 1988, we were 2, 3 or 4 participant laboratories, and this is the state in 2012. It is obvious that the number of researchers has an input on the numbers of publications that have been published each year. Here on the graph, you have those publications that are referenced by Science Direct and Springer Link with the keyword geopolymer. And it starts 1991. Everything that has been published before is not taken by the computers. And it is in 1991 my first official scientific paper that is cited everywhere, published in Journal of Thermal Analysis. It took some years to start, and then now it is an exponential increase. The book that I wrote in 2008 has now the 3rd edition that we launched last year. And the 2nd edition has been translated in Chinese. We have a lot of laboratories working in China. And this is the cover of the Chinese book. One major issue that I would like to briefly outline in this keynote is the opposition between geopolymer terminology and cement terminology. Why? Cement terminology applied to geopolymer chemistry, from my point of view, is an obstacle to the development of innovations in other fields of application. One group started resistance 2 years ago. It is the Geopolymer Alliance in Australia. The Geopolymer Alliance comprises several industry participants, big companies, including Alcoa, BHP Billiton, Rio Tinto, Rocla, and so forth, and the universities and the science providers are the major scientific institutions in Australia. One is missing. It is Melbourne University. They wrote in their website the following. Davidovits developed the notion of a geopolymer, that is a SiAl inorganic polymer, to better understand and to explain these chemical processes and the resultant material properties. To do so required a major shift in perspective away from the classical crystalline hydration chemistry of conventional cement chemistry. To date, this shift has not been well accepted by practitioners in the field of alkali-activated cements, who still tend to explain such reaction chemistry in Portland cement terminology. I give you one example that I found on the internet. It is a course on cement material for master students, in which you have the descriptions of regular Portland cement chemistry and then the geopolymer, and it is called in French alkali activation alkaline, for geopolymer in brackets. And they take the molecular chemistry that I am publishing, and this is how they present the chemistry of the geopolymer. This is fine. It is the copy of what I am writing in my books and on the internet. I don't have anything to remark on that. It is fine. I'm not against when one uses my terminology and my way of writing the chemistry, provided they cite the source and they cite the origin and they cite who is claiming that geopolymers are governed by this type of chemistry. After having shown the molecular chemistry of geopolymer, the problem is the following. They are adding the wording from a cement chemistry, and they said, well, a geopolymer is a dense gel that is called NaSAlH. Why? Because they rely on their Portland cement wording. That is, the end or the hardening of Portland cement is CSH for calcium silicate hydrate. And they say, fine, we just shift from calcium to sodium and we get NaSAlH for sodium silicoaluminate hydrate. This is wrong. We don't have an hydrate, we have something totally different. And I give you an example of why this is wrong, because it induces wrong information, granted ideas, and blocks any innovation. Last year, I had a visit from a German company that wanted to work on geopolymers, and the scientist, that was a cement scientist, asked me the following question. Professor, I don't understand. We know that in Portland, the end result is CSH, calcium silicate hydrate, and we know that Portland cement explodes when it is submitted to heat. It is not resistant to heat. It is because it has this hydration and these hydrates. So I don't understand. Geopolymer is also NaSAlH hydrate. Why does a geopolymer that is also an hydrate not explode when it is submitted to fire and to heat? I answered, well, this is your terminology that is wrong. The terminology of the hydrate induces in your mind that it will explode, like for Portland cement, whereas the entire structure of the geopolymer is totally different. We have hydroxyl groups, we don't have hydrates, we have a network, we have a macromolecular structure. The water, when it is at this temperature, has time to escape. And if we compare the behavior of Portland cement materials with the geopolymers, we see that everything that is CSH has no property above 300 degrees C, explodes. Anything that is geopolymer withstand the temperature. So it is very important to use the right terminology, and it is very important to learn the terminology. But cement specialists, or those who want to cope with geopolymer, are reluctant to go back to school. So we have a geopolymer terminology which is based on several units, and we are adding 2 new geopolymer units. This is what is published in the net. It is based on siloxo, polysiloxo, SiO, SiO, sialate, sialate siloxo, sialate disiloxo, and so forth. And we are adding a new one, the first one, aluminum phospho, ALOPO, polyaluminophospho. This is an aluminum phosphate-based geopolymer. You'll find the explanation at chapter 13 in my book by the 3rd edition. It has a beautiful macromolecular structure. The geopolymers, these are regular materials that are known by materials. We have here the aluminum PO4, which is called berlinite, and this is the structure that we get at ambient and low temperature. It is a succession, it is a spiral chain that is exactly isostructural to quartz. So we have POAl, O, POAl, no longer any silicon in it, and it is a 3-dimensional networking of spiral helical chain. And when this is heated above 900,000 degrees C, it transforms into tridymite and cristobalite structure, which is very, very precise. And it is the polyaluminophospho chains. We have done it, it works, and it provides wonderful applications and wonderful materials. There are several groups working on this material. The second unit is what I call the ferro-sialate. FAOSIOAL, polyferro-sialate, and is a substitution of the aluminum atom with iron atom. This is a chemical structure of kaolinite. We have the polysiloxo chain and branched aluminum hydroxyl groups. And the ferro-kaolinite has, instead of aluminum, 1 atom of iron. The substitution of aluminum may happen at most up to 25% of the entire structure. If we calcine this ferro-kaolinite at 700 degrees C, we get what I call the ferro-metakaolinite, FAMK 750, that is super reactive with the ferro-oxyl, like the aluminum oxyl, and this yields to a new material. The problem: scientific investigation of this material. Usually, to understand the macromolecular structure, the polymeric structure of geopolymer networks, we use nuclear magnetic spectroscopy. Here, with the ferro-sialate material, it is impossible because of the presence of iron that prevents the use of any NMR. So we have to shift to another system, to another method that is not well known, more complicated, and it is the Mörs-Bohr spectroscopy. So with the Mörs-Bohr spectroscopy, we'll follow the transformation of the ferro-kaolinite into the ferro-metakaolinite, MK750, and this is what we get They measure what they call the QS. This is the quadruple splitting QS. This is the ferro-kaolinite up 400 degrees C. You have an increase of the QS that is measured in minute per second, millimeter per second, and then up to 900. This is where we get this new group. And the geopolymer, that is polycondensed, is made of a structure that contains, it is a very simplified structure, the aluminum, no silent link, and the ferro link. The Moschbacher spectrum for ferro-sialate geopolymer looks like this. It is difficult to interpret. It is difficult to follow. This is one simplified one, and this is what we are looking at to detect the Fa double bond O SiO group and unit. Let us now look at new improvement in geopolymer technologies at large. The Journal of Pharmaceutical Sciences, Pharmaceutical Science, published this paper, Influence of Drug Distribution and Solubility on Release from Geopolymer Pellets, a Finite Element Methods Study. This is a group led by Professor Enquist at Uppsala University in Sweden, and they created a company that is called Orexo AB. What is the target here? They are taking MK750 metakaolin based geopolymer system. They are adding to the mixture their organic reactive molecule that constitute the drug. They harden and manufacture some pellets, tablets that contains very important drugs that are useful for long pain, long-term curing. The problem is the following. A geopolymer has the following property. It is acid resistant and microporous. So when swallowed, when it comes in the stomach, it is not destroyed by the stomach acid and released very gently the drug. So that they have at their disposal a pellet, a drug, that can release for a long period of time, maybe 1 day, 2 days, or 3 days, it is what they are studying, the drugs that are vital in order to cure people heavily cured with heavily pains. This is part of their paper. They have several papers. The parameters such as pellet size and composition may in the end be tuned to obtain an optimal microstructure and chemical condition for a safe and timely release from geopolymer pellets in oral administration of highly potent drugs, opioids, and the like. Let us look at patents. There are a lot of patents. This one is from a company that we know very well. It is a Polymeric. The title of this patent, Matrix, based on nanocrystalline cristobalite for thermal structural fibrous composite material. And the abstract, the invention relates to a matrix for thermostructural fibrous composite materials obtained by geopolymer synthesis based on nanocrystalline cristobalite. The nanocrystalline cristobalite results from the crystallization of geopolymer micelles by a thermal treatment at a temperature between 600 and 800 degrees C. And I show you, when you go to the site, a wonderful video doing. Okay, there is another patent dealing with composite, geopolymer composite materials. This one is slightly different. The title, A Heated Mold for Molding Polymeric Composites. The technology was presented in the US last year at the SAMP 2011. The SAMP is a very well-known conference and exhibition in the high-tech field of applications. It means Society for Advanced Material and Process Engineering. And their paper was titled Electrically Heated Ceramic Composite Tooling for Out-of-Autoclave Manufacturing of Large Composite Structures. We are dealing here with the manufacture of the huge wings that are on the windmills, power plants. This is a geopolymer composite tool, electrically heated, 15 meters long. So you see, this is not a small thing, and it needs a lot of expertise in order to achieve this. And this is the wing that has been manufactured in polymer, organic polymer system, demolded from the mold. Another patent from a US company dealing with different subject. Here we are in coatings and paints. Geopolymer and epoxy simultaneous interpenetrating polymer network composition and methods for the same related applications. The abstract, simultaneous interpenetrating polymer network, is composed geopolymer epoxy composition, and it is two-part component. First part, a waterborne epoxy curing agent, an aluminosilicate source, and amorphous silicate, and a second part, the epoxy resin and the alkaline silicate solution, and the two components are mixed to produce a SYNGE. This is a synthetic geopolymer epoxy composition that cures at ambient temperatures, and the compositions may be used as coatings, adhesives, mortars, casting material, and the like. Very interesting news from the state of Victoria in Australia. Sustainability Victoria, titled Rockwool Waste Briquette Plant. What it is. Australia's only manufacturer of rock wool insulation has found a way to capture, recycle, and reuse tons of waste generated from the manufacturing process. Rock wool is made from various rocks, such as basalt, limestone, and iron slag. The rocks are melted in a furnace to form lava that can be spun into fibers, generates 450 kilograms of waste for 1 ton manufactured. The project is using a geopolymer to bind the waste together. The geopolymer was developed with the assistance of chemical manufacturer PQ in Australia. The first of its type in the world, the plant was operational by March 2007, and in fact they put it on the web last year only. Using its own technique of geopolymer, the waste is bound and formed into little bricks, and the briquettes are fed back into the furnace and made into fibers for rock wool insulation. That is to say, the geopolymer is used to manufacture fibers. It transforms into fibers in the mix because it has the same constitution as the original basalt and so forth that are used to manufacture the rock wool. Another commercialized application is the production of facade elements made out of aluminum that contains a core in geopolymer. Geopolymer, that it claims a new standard in fire-rated facade material. It is sold in Australia and in the far southeast, but I know that the plant, the manufacturer, is in China. Another interesting news that I also mentioned last year, this is the following one. World Chemical Companies, BASF, launches Geopolymer product. This is the excerpt from our website. The Geopolymer Chemical Company PCI, Augsburg, the subsidiary of the World Chemical Company BASF, has launched a Geopolymer joint grout PCI for the general public. Meanwhile, the company is presenting the product in various international fairs and expositions. They started in Germany and then in the UK and presented it in Paris at the fair Batimat in November 2011. And they are mentioning the geopolymer technology. And it is interesting to follow the arguments that are outlined by the company technical brochures that are dedicated to this product. The French text is enthusiastic. On one page, one sees 3 women raising both arms above their head with placards that read "Abat le ménage, fini l'esclavage, down with the housework, end of slavery, joint propre pour tous, clean joints for everybody, Geopolymer forever." Thanks, BASF, for the good promotion. Let's continue. We have in Prague, in the Czech Republic, by the company Vodní sklo. Vodní sklo, vodní is water, sklo is glass, vodní sklo is water glass. It is the first geopolymer manufactured by a water glass company. Desilal geopolymer binder. It is a colloidal solution whose framework is very similar to zeolithic structures. These are the geopolymer structures. Let us continue now with geopolymer cement and concrete. I received an email that reads, "I would like to share the commercial success of our geopolymer technology for paving blocks and tiles from steel slag, fly ash, and ground brown furnace slag combination. The technology has been developed, transferred, and commercial production started, has produced around 0.5 million bricks, and got first purchase order of USD so-and-so and supplying. Finally, we are planning to have 10 commercial installations in India in coming 5 years. Dr. Sanjay Kumar, Principal Scientist, Resource, Energy and Environment, National Metallurgical Laboratory, Jamshedpur, India. Sanjay Kumar visited us, came to Saint-Quentin in 2005, and attended our Geopolymer conference in 2005, and had started to work on this type of application. And this is now where they are. Took 7 years, but this is a success for them. This is their brochure, paving tiles from steel slag, CSR, National Metallurgical Laboratory, Tata Steel, and it says a cement-free process. It uses eco-friendly geopolymerization process. I arrive now to a very crucial issue. You remember 1992, Rio de Janeiro. We have the World Eco Summit, climate change, CO2 emission, and so forth. Everybody was enthusiastic. Everybody wanted to work on the field. And we had 2012 Rio de Janeiro World Eco Summit, Rio plus 20, and everybody knows that we failed. In 1992, I started my study on CO2 emission on geopolymer cement in comparison with Portland cement, and I predicted the evolution of the Portland cement emission worldwide, and this is what I predicted, and this is what also happened. It's not a problem for Italy, USA, European production. They are still small. They do not increase. In fact, they diminished their CO2 emission. The problem is China, and the problem is India that is also coming. I also predicted in 1992 that the entire cement CO2 production will emit as much CO2 in 2015 as the European Union. The cement production, the Portland cement production, is one of the major CO2 polluters in the world. If we look at the world CO2 emission, 1992-2012, this is what we have. We have an increase of 50% of the CO2. Of course, the EU, European Union, had diminished its emission. The US have increased a little, China multiplied by 4, and the others more than 50%. So I thought that we could help, that we could propose a system. This was my hope, but in fact we failed. Nevertheless, some institutions have tried to understand and to focus on the costs and carbon emissions for geopolymer paste in comparison to ordinary Portland cement, to try to exactly define what is the difference in terms of environmental contribution. And this is a paper that has been published in 2011 by a group of Australian University, Curtin and in Queensland. And we read, examination of the life cycle cost and carbon impacts of ordinary Portland cement and geopolymers in an Australian context. Don't forget, this is the Australian context, with an identification of some key challenges for geopolymer development. Their conclusion, for typical Australian geopolymer product, there is an estimated 44 to 64% improvement in CO2 emission over OPC, while the cost of these geopolymers can be up to twice as high as OPC. However, those benefits are only realizable given the most appropriate source of feedstock and the least cost transportation. This is obvious for Australia, but it is also for other countries. The broad range of potential feedstock sources leads to a very wide range of potential impacts. Compared with OPC, emissions from geopolymer cement can be 97% lower if we use only waste that no more emit any CO2, up to 14% higher, depending. Each application for geopolymers therefore needs to be assessed for its specific location, given that the impact of location on overall sustainability is one of the determining factors, impact of location. To understand the basic parameters that are governing this issue, I will now mention something unusual and take some reference from our session in ancient technology. Why? Because we will have a good paper by Thomas Hantelcheck on pre-Portland cement and geopolymers. The paper presents the historical background of the 20th century technology of geopolymers in light of a literature research of the 15th to 19th centuries, and offers an hypothesis of why this historical knowledge was forgotten when Portland cement appeared. They continue. In the first half of the 19th century, we are actually dealing with a small or very small circle of experts, mainly formed at military schools, and therefore keeping certain secrets and specific knowledge as a part of the state's important matters. Well, this reminds me of something. We experience exactly the same situation today with geopolymer cement technology. We have small groups that keep everything secret, don't communicate with the others, do not mention, don't use the proper terminology in order to keep everything secret. This is exactly what we experienced, or they experienced, in the 18th, 19th century. This is what we have. But they say that the major obstacle, not even the experts were able to tell whether local materials will suit the constructions or not. The physical methods of qualifications were not sufficient, as well as chemical behavior. This was 200 years ago. It is no longer. We are different, but the behavior is the same. So we keep the knowledge that we got from our scientific investigation. The uncertainty of results, the necessity of permanent study of the local material used for construction, and the search for the proper proportions and technology were the main reasons of the decline of the lime-clay combination that was used at that time when Portland cement appeared. Everything seems to be more sophisticated, more complicated than the simple use of standard Portland cement in an admixture with pebbles and water. So when I started and when I developed some of the geopolymer cement, I was proud to answer to the question, well, how do we be sure that we will produce geopolymer cement everywhere in the world? I said, no problem. We have so many possibilities. There are so many rock-forming materials that will be suitable to make a geopolymer cement. It will be very easy. It is not. Because the transfer technology, transfer knowledge is not so easy. You have a couple of people like myself and others that have the knowledge, and that's all. So it is too complicated, which means in order to cope with the issue, we have to establish standards for the global economy. In my book, we have, for example, for cement, a list of several raw materials. Everybody is proud to publish, well, I made geopolymer cement with this type of waste or with this type of material and so forth. This is not the way to promote the system if we want to save the world. If we don't want, it's okay. So establish standards for global economy, and I'm proposing, from my point of view, we should have maximum 2 universal and user-friendly geopolymer process. The first one, based on fly ash. I explain later. The second one, based on ferro-sialate. And of course, we need an industrial hardener, based on geology. So you see, we have one, an industrial waste, fly ash, second, geology. The first criteria is user-friendly. What does this mean? In chemistry, we know these posts, signs, corrosive and irritant. The corrosive materials are user-hostile systems. The irritant materials are user-friendly systems. And if you want to know what is hostile and friendly, look at the table. Columns hostile, you have quicklime, NaOH, KOH, sodium metasilicate, SiO2 Na2O ratio 1, any soluble silicate with a molar ratio less than 1.45. And in the friendly column, you get slaked lime, Portland cement, iron slag, a slurry that has a molar ratio between 1.25 and 1.45 that contains kaolin, because kaolin is a protective material, and of course any soluble silicate with a SiO2 M2O ratio higher than 1.45. This is very thoroughly explained in one chapter of my book. So let us come back to the standards. First, sodium, potassium, calcium based fly ash based geopolymer cement. I always was skeptical about fly ash, and I only studied the fly ash in the years 2005, practically 20 years after starting geopolymer cement. We had a European project that I was involved in, and I started to look at. For me, fly ash was not a relevant material in terms of raw material for geopolymer cement. But nevertheless, I published in 1994 in an American scientific magazine, World Resource Review, under the title Global Warming Impacts on the Cement and Aggregate Industries. Third world development means implementing the use of electricity and building infrastructures and houses. In short, electricity and concrete. The byproduct of electricity production with coal firing is fly ash. The innovative step would be to produce electricity and low CO2 cement, geopolymeric cement, in the same plant by adapting and implementing fly ash production into geopolymeric raw material without any supplementary chemical CO2 emission. This is what I envisage. I say, look, this would be a great innovation, provided the power plants, utilities are also tackling the problem and just changing the way they introduce their coal, the way they burn it, and so forth. I know that it is feasible. But at that time, everybody was telling, well, coal is emitting a lot of CO2, so usually, normally, the use of coal to produce electricity should decline. So I was not interested in working on fly ash. I was wrong. The problem is the following. World energy sources, oil declined, but coal declined at the beginning, but then now it is increasing by 25% within 1 decade since 2002. And this is the trend will continue. And this is due to the BRICS country, Brazil, Russia, India, China, South Africa. So coal use for power, for producing energy is becoming important, which means fly ash is important. And the majority of studies that are done in India, for example, on geopolymer concrete are based on fly ash. So we have to cope with coal fly ash geopolymerization. But not at 60 degrees C, not at 85 degrees C, and so forth. It must be a cement. For me, a cement is something that hardens at room temperature. Otherwise, it is something different. It is a binder, or it is a resin, but it's not a cement. So any system that is developed that requires temperatures is not. Well, they say fine, for precast, good, but this is not what we are looking for. We want mass production. Remember, we want to save the world. The majority of those who are studying coal fly ash, so-called geopolymer, are in fact doing alkali activation of the fly ash, and we are comparing now the alkali activation of fly ash with the regular, genuine geopolymer fly ash. The conventional method means alkali activation, which means dissolution of the fly ash. This is the main objective. We have to dissolve the fly ash in order to get the Si and the aluminum cations in the mixture so that they can polycondense and make the geopolymer. So we get zeolite. So we use concentrated caustic soda or very strong sodium silicate solutions with a high degree of alkali in it, curing at 80 degrees C. This is the user hostile system. More than 50 or 60% of all papers dealing with so-called fly ash geopolymer are proposing a user hostile system, and this is wrong. The geopolymeric methods is a room temperature hardening. It involves the polycondensation. We use the fly ash. I prefer potassium silicate solution. We use blast furnace slag as the geopolymeric precursor, water, and it is user-friendly. It is a cement. If we compare the compressive strength with the alkali-activated fly ash in light blue and the geopolymer fly ash in dark blue for 5 different fly ashes, the geopolymer is always higher in strength. Here, these are the 15 fly ashes that of our GeoAsh European program. We got 4 that experienced flash set because they were class C, lot of calcium, free calcium in it, and they could not be used in our system. All the others are providing medium to very high strength. The second system, based on geology. And of course, it must be a geology that is available all throughout the world. Otherwise, this is nonsense. If we only have in one remote part of I don't know, the island of Canary Island, for example, it doesn't mean anything. So it is the ferro-sialate based geopolymer cement that I am promoting industrially, and it is based on a new patent that is called Geopolymer Cement of the Calcium Ferro-Aluminosilicate Polymer Type and Production Process. The abstract, binder and cement of the ferro-aluminosilicate Fa or SiOALO geopolymer type with some of the Al atoms substituted with Fa atoms, the whole satisfying the following raw formulae: calcium, sodium, potassium, FAO, SiOLO, and SiO, with the ratio. This geopolymer binder result from a calcium geopolymer type geopolymerization. That is to say, we had a regular geopolymerization slag-based within the system and ferro-metakaolin FAMK 750. So we get what I call ferro-sialate-based geopolymer cement. Of course, it contains iron, high amount of iron. And because it contains a lot of amount of iron, it is red. Well, is red ugly? Are bricks ugly? And so forth. I guess the red bricks are better than the dark gray ugly cement, Portland. So this is not a drawback. On the contrary, on the opposite. So this is not theory, this is practice. It is in development by the company Bana UK in Northern Ireland. What you have is here, it is close to the very well-known giant causeway, basaltic giant causeway, and Andrew McIntosh will have a presentation tomorrow morning on the material. What is interesting with this system is that we will find it practically all over the world. There must be some adjustment, same than for Portland cement. People at manufacturing Portland cement need limestone, calcium carbonate of a specific, and if they don't have, they manage to get the right formulae by adding system, but only based on their local geology, and we will also often, I hope, be able to do it all over the world, provided people work with us and develop it. But from a pure geological point of view, this is a material that we can get practically everywhere, and that has not been used so far for several reasons. The third element is the industrial hardener. In powder form, based on geology. It must be a user-friendly powder form will emit a molar ratio 1.45 at most. It must be lower. I don't want a mixed made of powdered silicate that has a very low ratio and NaOH flakes. You'll find in the literature a lot of papers describing, I have invented a dry mix for geopolymer cement. And when you look at it is potassium or sodium hydroxide flakes ground with metasilicate and so on and so forth. And this is user hostile. I want innovation. Yes. I'm presenting here an excerpt of my keynote 2009 on that subject. This is a short keynote. So we will discuss the practical problems that are connected with the mass production of geopolymer cement. So you remember we said we have two key issues to tackle the problem of mass production. Millions of tons. The bulk silico-aluminate material is easy to get, but the alkali silicate system is not easy to get. So we have to make a system in powder form that will supply in the mix a low pH, a user-friendly system. I don't want a powder form that is made of NaOH, powdered, or metasilicate, molar ratio 1:1. I want something that has a molar ratio of 1.4, 1.5. The system that we have experienced is what I call the artificial basalt, which is could be alkaline slag. Instead of having calcium slag, we have alkali slag, and from a geological point of view, it is a basalt. This is in the chapter 24 in my book, and I sum up it very briefly. So we manufacture a basalt at 1200 degrees C, 1250 degrees C, or 1300 degrees C. That is to say that manufacturers are accustomed to and go through the furnace route. We don't change anything, just the raw material is different. The strength at 28 days, depending on the geological raw material that was used to make this basalt. These are geological material that contains naturally a very high amount of potassium in it. These are volcanic tuffs that have up to 10% by weight of K2O and a certain amount of Na2O also. So this is, we select the geology in order to get the maximum of potassium in our system. And you see at 8 days when you have 30 MPa for the LaO1, this is a volcanic tuff up north of Rome in Italy, whereas the GC, it is from the Gran Canary Island volcanic tuff. We achieve at 8 days 30 MPAs and more than 45 at 30 days. So this is a good material. How is it manufactured? This is a system, which is what it is. Here we make the glass, the basalt, take the volcanic tuff, we add the additives, calcium, sodium, potassium, in order to get the right formula that we want. We grind, we vitrify, we quench, and we have the alkaline glass, and we grind. And we say, oh well, since we need the heat here, why not take the heat to calcine the kaolin to make metakaolin? This is just a suggestion, it is not mandatory. But you see, this is practically the same way of making the silicate today. Only the raw materials are changing and the quantities will be totally different. So, this has been a work that we have done in 1995-97, and our friends in Melbourne are trying to cope with this, and they are proposing something different. They take albite, that is a sodium aluminosilicate, and they add NaOH or sodium carbonate at 1000 degrees C, and they also get 44 or 42 MPa at the end. Last part, very briefly, geopolymer and archaeology, briefly because we have our session this afternoon. I guess some of you know my last book, Why the Pharaohs Built the Pyramids with Fake Stones. It is a theory that is supported by a lot of institutions in the world, renowned colleagues. And the last paper was published in 2011, where the casing stones of Seneferu bent pyramid in Dashur, cast or carved, nuclear NMR evidence, and it is by Mackenzie and so forth from New Zealand, Warwick University in the UK, New Zealand, and Drexel University. What is here, what they got, they studied the casing stone of this pyramid, the bent pyramid. What we have, this is the bent pyramid, closer, and we closer and we will see the casing. These are huge blocks. And they write, a comparison was made of 29 Si, 27 Al, and 43 calcium, mass NMR spectra of the outer casing stone from Seneferu bent pyramid in Dashur, with 2 quarry limestones from the area. The NMR results suggest that the casing stones consist of limestone grains from the Tura quarry, so we have natural limestones that are cemented with an amorphous calcium silicate gel formed by human intervention by the addition of natural reactive silicae, diatomaceous earth from the Fayum area. All of our projects on Egypt and related technologies are on standby because of the political situation. We have been studying ceramics, low temperature fire styles. This is on standby, that are 5,000 years old. Cements, waterproof cement that were used for cisterns, colossus, and we have also on standby some megalithic stones. This is the end of my State of the Geopolymer R&D 2012.